Hi, my name is Thibaut Véron, and I am going to present the recent work that we did with Xavier Caruso and Tristan Vacon on adapting signature-based algorithms to the computation of Gröbner Bases over Tate Algebras. The general context is effective algebraic geometry. It is a known fact in algebraic geometry since the 50s that there exists a bridge, a correspondence between the concepts of algebraic geometry and those of analytic geometry. This goes for the geometric objects, the varieties and the manifolds, as well as for the underlying representation, the systems of equations involving multivariate polynomials on the one hand, and the analytic functions, that is, multivariate power series with a convergence condition on some open ball, on the other hand. This correspondence is one of the pillars of modern algebraic geometry, and it has led to a lot of results. Another important contribution of modern algebraic geometry is that it is ubiquitous, allowing to use geometric tools for objects which are very different from usual manifolds over R or C. For instance, in applications in number theory, one may want to work over different extensions of Q, such as p-adic numbers, and algebraic geometry does give geometric tools for studying those objects. The previous bridge inherently relies on the fact that the Zariski topology is coarser than the usual Euclidean topology, and in particular, that it is compatible with the usual metric. On the other hand, in a p-adic setting, the metric and the topology look very different, and establishing a bridge with analysis required a different approach. Such a bridge was identified by John Tate in 1962 and led to the construction of so-called rigid geometry. The main objects of study of that field are Tate series, that is, multivariate series with a convergence condition on the closed ball. We are interested in effectivity questions. Both polynomials and analytic functions can be manipulated algebraically using exact algorithms. For example, for polynomial algebra, one has a variety of tools at its disposal for manipulating both objects and systems of equations, which allows to perform geometric operations with computer algebra software. An example of such tools is the theory of Gröbner Bases, which allows to compute, for example, the sum and the intersection of ideals corresponding to intersections or union of varieties. This tool has also proved indirectly useful for manipulating analytic functions, both in their representation and in their equations. When we started working on this topic, our goal was to develop similar tools for Tate series, the Tate's p-adic analog of analytic functions. It turns out that those objects behave actually a lot more like polynomials than like analytic series, and we were able to develop a theory of Gröbner bases for Tate series, as well as implement algorithms to compute them, such as Buchberger's algorithm. The work that we present today is the adaptation of modern computational and algebraic techniques, namely signatures, to make those algorithms more efficient. Before moving further, let me recall what Tate series look like and how we can work with them. In its simplest form, the definition is that they are multivariate power series with coefficients in a valued ring with some convergence condition. Let's go over this definition point by point. Starting with the coefficients in a valued ring. So such rings are like the p-adic numbers or power series rings. And elements of such a ring can be seen as some series in some element pi, called the uniformizer of the ring. For the previous example, it would be p and x, respectively. And elements can then be given a valuation that corresponds to the number of zeros, of initial zeros there are in that series representation. So this picture with balls is the general picture to keep in mind when working with elements in a valued ring. More generally, we will be looking at terms in a series ring, that is the product of one of those coefficients with a product of variables, which we can view in such a condensed form. Series themselves are then sums, possibly infinite, of such terms. The convergence condition is then that we want the valuation of the coefficients to go to infinity, or equivalently, that in the series, there are only finitely many terms of a given valuation. For instance, polynomials are Tate series. The sum of pi to di x to di is a Tate series. In both cases, the valuation increases, but the sum of x to di is not a Tate series. The valuation is constant. So those are objects of study, and we wanted to develop a theory of Gröbner bases on those objects. But we have to be a bit careful. We are working with finite precision objects, and Gröbner bases are known to behave quite badly with finite precision objects. That's for mainly two reasons. First of all, successive losses of precision can accumulate. And second of all, Gröbner bases algorithm require to identify leading terms of elements, and this requires testing whether a coefficient is zero or not. The first problem is not really one when working with valued rings, because errors do not naturally stack. As for the second problem, we solve it by defining a term ordering So an ordering taking into account both the monomials and their coefficients, which will be such that terms which are close to 0 will be smaller for the ordering, and in particular cannot be the leading term of an element. To do so, we compare terms with their coefficients by first comparing the valuations, and then breaking ties using a usual monomial ordering. This ordering has several properties. First, as we wanted, terms with smaller valuation are larger. It means that if we cannot test whether the leading term of a series is 0, it means that we cannot test whether the entire series is 0. Another property is that we can have infinite sequences of reduction for this order, but in such a sequence the valuation will go to infinity, and since we will always be working with bounded precision, in practice reductions will terminate. And finally, one last key property of a term ordering is that all elements must have a leading term, a largest term. And this is guaranteed by our hypothesis on the series. Since there can be only finitely many elements with minimal valuation, one of those elements has to be the largest for the monomial order, and this will be the leading term of our series. So all in all, this term ordering is suitable for defining Gröbner bases. Those Gröbner bases can then be computed using the usual algorithms, such as Buchberger's algorithm. It's a very classical algorithm. You take the elements from your input, you put them in a basis, you combine them to form S polynomials to eliminate the leading terms, and then those S polynomials you reduce, and if the result is non-zero, you add it to the basis and you form new S polynomials to add to the list of weighting S polynomials. This is what we have done last year and presented last year. And the problem from there is that this algorithm is not always as efficient as we'd hope. In particular, reductions turned out to be a very expensive step. Now that is okay if the reductions are necessary and the result is added to the basis, but some reductions are not necessary. If the result is 0, it is thrown away. This is already the case for the usual algorithm in the polynomial case, but in our case there is an extra bit of difficulty. Since our reductions to 0 are infinite sequences of reductions and only stop when we reach the precision bound, the more we increase the precision, the more expensive those reductions to 0 get. So we really want to avoid those reductions to 0. How do we proceed? Well, let's look back to the polynomial case for a moment. As I just said, the same problems appears there, and solutions have been proposed. The main idea behind those solutions is that some reductions to 0 can be predicted, regardless of the polynomials that we are working with. For example, if in the course of the algorithm with input f1, f2 to fm, we compute the polynomial corresponding to f2 times f1 minus f1 times f2, this polynomial will be 0. And the same is true for sums of such polynomials. The natural idea from there is to keep track of where the polynomials come from so that we can identify such situations. In other words, we want to keep track of the coordinates of the polynomials in terms of the input polynomials, and those vectors of coordinate live in a free module of rank m over the polynomial algebra. This idea was proposed by Müller, Morin and Traverso in 1992. And it works. Such reductions to 0, they are called syzygies, will be identified by this process. But keeping track of that representation on top of the actual polynomial now requires m plus 1 polynomial addition, where before only 1 was required. And this extra cost makes the whole algorithm impractical. A natural idea from there is to keep only some terms of the module representation. Then, those polynomial additions become simply term comparisons, and still allow to identify syzygies by comparing them with the leading terms of some known syzygies. But sometimes the leading terms of a sum cannot be computed just from the individual leading terms. If the two leading terms are the same, we don't know what the result is. The final idea was what led to the idea of signature-based algorithms itself, and it was in Fogger's paper from 2002. The idea is that we don't need to do those operations. By itself, the fact that we would be adding module elements with the same leading term means that we would be doing something redundant and that this operation can be skipped. So in practice, how does it translate to the algorithms? Well, instead of working with polynomials, we will be working with pairs composed of a signature, that is the leading term of a module representation, and the corresponding polynomial. And we can operate on, typically add such objects, only if the addition is regular, namely, if there is no collision on the signature. As we said just before, this is a necessary condition to be able to compute the signature of the result. And in this way, we will define regular S polynomials, regular reductions, and the algorithm will be restricted to those regular operations. Note that all of this requires having an order on the signatures. We will come back to that in a few moments. I would just like to note that this line of algorithms has given rise to a lot of research in the past 20 years, and an extensive survey can be found in the paper by Ida and Foggia from 2017. And just to give an overview on how many algorithms have been developed, you can see some examples on this picture from 2013 produced by Ida. So with those ideas, here is what Buchberger's algorithm becomes with signatures. Not much is changed, but now the polynomials are labeled with their signatures. We have to take them by increasing signature order, and we restrict to regular operations. So in practice, how does it work? First, we take our input polynomials, we give them their signature, the elementary module elements EI. Then we put them all in G, and we form S polynomials from those. Note that at this point, all S polynomials are regular. Then at each step, we take the element with smallest signature from P. We regularly reduce it. Note that its signature does not change during the process. And if the result is non-zero, we update G. Then we form S polynomials. If they are regular, we add them to the basis. And if we are not, and note that then we cannot compute the signature of the results, we don't add them to the basis. But if we can add them to the basis, if they're regular, let's see what happens with the signature. By definition, the signature of the S polynomial is larger than the multiple of the signature that we started with. Which means that if the order on the signature is compatible with the order on the polynomial ring, and in particular if 1 is the smallest monomial, the result will always be larger than the signature we are currently processing. So all the signatures in P will be larger than the one we are currently processing. Basically, by just ensuring that the order on the signatures is compatible with the monomial order in the polynomial ring, we can ensure that signatures are increasing throughout the algorithm. And this is the key fact in ensuring that the algorithms work. So now we know what we need to do to pick a signature order, and there are not too many restrictions. As long as the signature ordering is compatible with the monomial ordering, it will give a loop invariant for the algorithm. One of the easiest examples of such orders is the position over term ordering. First, you order the index I of the signatures, and then you order the terms. It satisfies all the properties, and it does give a valid signature ordering. So now let's come back to the algorithm, and remember that the signatures are increasing throughout the algorithm. It looks like this. First, we are considering all the signatures in E1, then all the signatures in E2, then all the signatures in E3, and so on. And for the polynomials, it means that first we compute a basis of F1, then of F1, F2, then of F1, F2, F3, and so on. For this reason, this is known as an incremental signature ordering. And this algorithm, with additional criteria, is known as the G2V algorithm, from the name of its authors, Gao, Guan, and Volny. A big advantage of incremental algorithms is that the main loop can be split in two. You consider the polynomials one by one, and then you process them using the usual loop. And then some intermediate optimizations, which would not necessarily be compatible with the signatures, can be applied at the end of the inner loop. So now we can go back to our series. The first algorithm that we presented in the paper is this algorithm using the position over term ordering. This ordering is still compatible in the Tate setting with the base term ordering. It is still incremental, but there is one difficulty now. We cannot ensure anymore that the signatures do not decrease. Here's an example. We take a polynomial from the basis, a polynomial from the queue of pairs, and we take the S polynomial. It is regular, but in this case the signature has a larger valuation, so now it is smaller. That's because when computing the S polynomial, we needed to multiply the first polynomial with something with positive valuation, and the result can only be smaller. This is a legal operation. We cannot forbid it, and it is known as signature drop. It would make the usual proofs for signature-based algorithms not work. Why does it happen, and why didn't it happen in the polynomial case? That's because our term ordering does not share a key property of the monomial orderings for polynomials. Those orders are global. That is, all monomials are larger than or equal to 1. And most signature-based algorithms rely on the fact that the order is global in order to have this loop invariant by signatures increasing. Recently, in 2018, Lu et al. Proposed a signature-based algorithm for so-called local orderings. That is, orderings where all monomials are smaller than or equal to 1. But our ordering is also not local. It is what is called a mixed ordering. Some elements are larger than 1, and some elements are smaller than 1. But even though we cannot prove that the signatures are increasing, we could adapt the proof of the paper for the local case to our mixed case. The idea of the proof is indirect, but it follows the same scheme of proving that some other quantity taking into account both the signature and the leading term of the series is increasing throughout. Interestingly enough, the 2018 paper requires another ordering, the term over position ordering, in order to work, while our algorithm and our proof works with the incremental ordering. I will be more brief about it, but we also propose another algorithm using another ordering, the so-called Vapot algorithm, first taking into account the valuation of the coefficients in increasing order, then the position, and then the terms. This order is not compatible with the monomial ordering on the Tate series, but it is an analog in valuation to the degree of opposition over terms ordering used by the F5 algorithm, with the same idea that we want to delay as much as possible the computations of objects which should appear late, typically, in our case, objects with high valuation. In practice, it means that we compute elements with non-decreasing valuation, and we can split our loop further with an outermost loop on the valuation of the elements. And this algorithm is also interesting because it brings back the computations to the level of the residue field, the finite field with p elements in the case of p-adic numbers. Because the two inner loops proceed exactly as would the same algorithm over polynomials over this residue field. And it also opens the way for more optimizations at the interface between the loops. So to conclude, what we have presented here is two algorithms computing Gröbner bases on Tate algebras with signatures. Those algorithms are using two different signature orderings and are either incremental or semi-incremental. I didn't speak about it, but it is a fact that generically those algorithms behave exactly in the same way. Namely, the outmost loop in Vapot is used only once. The valuation never increased throughout the algorithm. We have implemented both algorithms in Sage, and they are now distributed with Sage since version 9.1. Experimentally, they usually appear to be significantly faster than Buchberger's algorithm. I show here several examples, so in each case it is one system, taken randomly with some constraints, computed with different levels of precision, and we show the time taken in terms of that precision. The blue curve is Buchberger, the red one is Pot, the teal one is Vapot, and if the curves are cut, it means that it would go outside of the graph. Here we have the situation that I said was the usual one. Both curves are the exact same, but they are lower than Buchberger. Here is another example of the same thing. And now in future work, we would like to better understand the corner cases, those non-generic situations, because here it looks like everything can happen. For example, here we have an example where Vapot is faster than Pot and a lot faster than Buchberger. Here we have an example where when Pot is faster than Vapot, but Buchberger is also faster than Vapot. And here we have a situation where Pot and Vapot are doing the same thing, but they are slower than Buchberger for large precisions. So we need to understand those situations better to see if it means that we should improve the implementation or implement heuristics to decide between one algorithms or the other. That would be if the difference comes from theoretical reasons. Similarly, a lot of the possible optimizations that we can think of, for example, between the loops in the algorithms, are not so clear-cut. They don't always bring improvements, and we would like to understand them better to decide algorithms on when to apply them or not. And finally, we would also like to work on improving the basic arithmetic, and in particular the complexity of the reduction algorithm, to flatten this dependency on the precision. Ideally, we would like to reach a point where the complexity exponent is fixed and does not depend on the system. For that purpose, we would like to see if we can use techniques from fast arithmetic to accelerate the reduction step. The main observation is that the terms which appear when working with Tate series are very different from the ones commonly seen with polynomials. In particular, with our ordering, it's not unusual to see series of extremely high degree but small support appear, and they need to be reduced by smaller series, and decreasing the degree one by one is not fast enough. Anyway, that's it. Thank you for your attention.